Okay, so we've had a lecture on independent samples. So when we maybe are comparing genders or two races, but now we want to talk about what happens when we have dependent samples. And sometimes for students it can be hard distinguishing between independent and dependent samples. So I would do your best to go through this video slowly, maybe even listening to it twice, to see if you can pick up on the pattern of what makes dependent. Okay, paired T. All right, so if we have two samples, why do we need to differentiate between independent and dependent samples? Why not just run an independent two-sample t-test? All right, so let's follow that incorrect logic for a minute. So here's an example where we have, we want to look at shoe wear, and each person wears an Adidas for a while, and then each person wears a Nike for a while. And we want to see if there's a difference between the Adidas and Nike shoe wear. All right, so we want to see if the two shoe brands provide the same results on average. So we want to set up our null and alternative. So we'll have maybe mu Nike equal mu Adidas and mu Nike not equal to mu Adidas. All right, and we want to get our p-value, and here let me show you how to do that. You know how to do that already in JASP. But let's run it. So we've got, notice here I've got the data as it appears in the PowerPoint, but for us to run independent sample in JASP, remember we need our categorical column and then our quantitative column. So I'll go into t-test independent samples, and I will put in the wear as the dependent and the shoe brand as the grouping. All right, and we can do our equality of variances check. They are, we can assume they're equal, so we run student, and we've got we're just testing not equal to. And we see that the p-value here is 0.737, all right? So let's go back over here. So we've got 0.737 or 7375, and you guys know what to do with that, right? Life's on repeat. All right, so with our p-value of 0.7375, that's clearly greater than alpha, so we fail to reject the null. All right, so we do not find a significant difference. All right, so we cannot conclude that the two shoe brands differ on average. All right, so we could bebop along thinking that Nike and Adidas have basically the same wear. All right, well, what's wrong? All right, what's wrong with just doing it this way? All right, well, one thing that's wrong is that we did not detect a difference. But what if a difference is actually there? We just didn't detect it. And the reason we didn't detect a difference is that we picked up differences between the people and differences between the shoe brands. All right, so by doing an independent sample t-test, we're getting two types of differences. All right, and let's go back for a second. All right, so let's go back and look at our data. What do I mean by that? Well, think of person one here. For person one, we are picking up the difference between the Nike and Adidas that they wore, okay? But we're also picking up all the vertical distance, which is all the differences between the people, right? And so think about this. If you want to test if Adidas and Nike have the same shoe wear, do you really want to test the difference also between how different people wear those shoes? And the answer is no. You just want to kind of isolate for a person, do the Adidas and Nike differ, right? We may have one person who's very heavy-footed and they stomp around, and so they wear shoes very heavily, whereas we have another person who is kind of light and flighty and tiptoes and hardly gets any shoe wear regardless of the Adidas or Nike. we don't want to pick up those differences in the people. We only want the differences between the Adidas and the Nike for each person that wears them. So let's go all the way back now. All right, so again, we don't want those two differences. We do not want the differences between the people. All right, so we need to conduct a test that excludes or ignores the variation due to people. All right, so how do we do that? And the answer is we analyze as a paired t-test. So the Adidas and Nike are actually dependent samples because the same person wears both of them. All right, and so rather than thinking that the Adidas comes from a population with mu Adidas and the Nike comes from a population with mu Nike, what the software is going to do, so again, this is what the software does, this is not what you do. The software calculates a difference for each person. All right, well, why is that important? Well, now we've gone from 2 columns of data to basically a single number for each person. All right, and on this column, we're going to calculate a sample mean difference. So this 0.02 here would be the sample mean difference. And we're going to compare this sample mean difference to a population with a mean of 0. Okay? All right, so now our hypothesis test looks a little different. Now we're going to have just a mu sub d, where d stands for difference, equal to and not equal to 0. All right, it could also be, we could also test alternatives of less than 0 or greater than 0, and we'll talk about those in just a minute. All right, but here, this is just a simple two-tailed test. All right, but the key here, and again, I'm going to say it one more time, we no longer are comparing two means. So we're no longer comparing mu Nike to mu Adidas. We now have a single mean difference that gets compared to 0. Okay? All right, and so let's talk about how. Let's go back over to JASP and talk about calculating this paired t. So we go into paired samples t-test. All right, and we're interested in our Adidas and our Nike. All right, we're going to leave it on student because Wilcoxon signed rank is for when we have non-normality, and so we're going to assume normality for anything I give you for right now. Our alternative is not equal to, so we can leave it on the default. All right, and let's go ahead and check our effect size because we're used to that from the last video. All right, so here we go down here and we see that our p-value for Adidas and Nike is now 0.032. All right, so 0.032. All right, so now with that p-value, we see that we do have a p-value less than alpha. You guys know what this means. This means we reject the null, and thus we conclude that the two shoe brands do differ on average. Aha! So we ran a different test, and now we have significance. Why do we now reject the null? All right, so for independent samples, the p-value is 0.7375. because there is more variation or uncertainty. Okay, so variation and uncertainty or error are synonymous. All right, so this represents two kinds of variation, all right, that I talked about a minute ago. We have the variation between the shoe brands, Nike and Adidas, but we also pick up all that vertical variation between the people. In the paired t-test, the p-value is 0.0319 because by consolidating to a single mean difference or just calculating the difference for each person, it represents one kind of variation, which is brand. All right, so we're able to isolate just the variation in Nike and Adidas. All right, so what are some advantages of using a paired T? You're probably already thinking about a couple of these. One, of course, we removed the effect of the variation between people. And what did this do is it increased the sensitivity or the power of the test. We went from not detecting a difference to actually detecting a significant difference. All right, so we were able to finally, with the paired T, conclude that Nike and Adidas do differ in how shoes are worn. All right, so let's go back out of here for a second and just talk about the effect size, just making sure you can interpret this. So we see here that our effect size is negative 0.8. All right, so what negative means, all right, is that the effect is reduced, all right, by our treatment. Our treatment here would be Nike, all right? So Nike has less wear than Adidas. And what is the size of the difference? What is the size of this effect? And the answer is 0.8. And 0.8 we would interpret as somewhere between a medium or large effect size. Right, so when do we want to use a paired t-test? All right, when we have both populations within each test subject. All right, so this would be exactly what we just had. I know that sounds a little confusing, but what that means is that each test subject would be, say, a person. All right, and each person participates in both of those populations. So in this situation, it would be the person wearing the Adidas for a while and then the person wearing the Nike for a while. All right, so another example would be measurement, intervention, measurement. And this is probably our most common time that we used paired T. This is certainly the most popular for when I use paired T in my own analyses. A lot of the research that we do in education are interventions. And so we would have this pre and post measure to see the effect of the intervention. All right. Another example would be match or paired observations, which is what we saw with the Nike and Adidas example, that the observations were matched or paired by the person. All right, but the biggest reason to use a paired T would be we want to remove variation between test subjects. Another example that I recently saw when I was reviewing an article was we had families with siblings, and one sibling was visually impaired and another sibling was of normal vision, and we wanted to test the perceived motor competence between the siblings. And so we have all these families with these siblings, and this was an example where we had matched or paired observations because we didn't want to measure the perceived motor competence differences between all the different families. We just wanted to see if there was a difference between the sets of siblings. All right, so again, another example for a paired T. All right, and let's go through some more examples. All right, let's say we want to compare 20 tires of brand A with 20 tires of brand B. All right, so what do we want to do here? We do not want to consider the differences in cars, right? A lightweight sports car is going to wear tires very differently than, say, a very large truck. All right, so we would want to use a paired t-test, putting each brand of tire on each car. So much like the Nike Adidas example, a car would drive around with brand A for a set time, and then the car would put on brand B and drive around again for that same set time. All right, and then we would combine the results across all the cars. All right, another example. We want to compare 10 appraisals from company A with 10 appraisals from company B. All right, what do we not want here? We do not want to consider the difference in values of the homes, right? We just want to know if the companies are appraising differently. So what would we do? We would use a paired t-test and let each company appraise each house and then combine the results across the houses. All right, so let's do another one. The lab wants to compare two methods of testing chemical concentrations across the expected range of a typical product. The two methods are visual titration, VT, and automatic titration, AT. 10 samples were tested using each method. The data in parts per meter are given below. Does the data indicate a bias between the two methods? All right, and we're going to use our standard 5% alpha. All right, so what we don't want the differences in the samples, right? Because we see here's a sample 11 and 14, here's a sample 91 and 93. We don't want those differences. We just want the difference between the VT and the AT. So notice when we calculate the differences of each row, all right, all of our differences are much more similar than the differences in the VTs or the differences in the ATs, all right? And that's what I mean by here we are isolating just the difference between the two methods and not the differences across the samples. All right, so let's go back to JASP and actually run this before we take a look at the results. All right, so we would want to we could get rid of our Nike and Adidas, and now we want our VT and our AT. We've got our student test. Here again, we're just measuring a difference, and we can calculate our effect size. All right, and we see our p-value down here of 0.022, and we see our Cohen-D effect size. All right, so let's go back now to the PowerPoint. And here is our null and alternative. So we've just got mu d equal to and not equal to 0. So one thing I'm going to ask you to do in Blackboard is to also define your difference. It's not as important when we're dealing with a two-tailed test, but we will see examples of one-tailed tests especially in the classwork video that you'll probably watch next. All right, and so it's important to define the difference. So here we put VT in first and then AT. All right, and so our difference would be VT minus AT. All right, if we put in AT first and then VT, our difference would be AT minus VT. All right, but we saw that our p-value was 0.0220, so we reject the null. All right, and we conclude that the two methods do, in fact, give significantly different results. All right, so at this point, I think you're ready to watch the classwork and to actually start interpreting some of these problems on your own.